Hello everyone. Today we are going to derive the expression for force matrix of a quadratic Bohr element. We have already derived the expression for shape functions of a quadratic Bohr element and also the expression for stiffness matrix of a quadratic Bohr element. If you have not watched those videos, I highly recommend that you please go back and watch those videos so that you can easily wrap your mind around how we actually get the force matrix of a quadratic Bohr element. So to begin with, I have to write the expression for weak form of the governing differential equation of a Bohr subjected to uniformly distributed load and a point load. Okay, so this is the expression for weak form of a Bohr element. It is integral over the limit 0 to L. It is AE into du cap divided by dx into dw suffix I divided by dx into dx is equal to integral over the limit 0 to L. It is wi into q into dx plus wi into AE into du cap divided by dx over the limit 0 to L. We derived the stiffness matrix of a quadratic Bohr element by operating on the left-hand side of this particular weak form expression. If you just operate on the left side of this particular weak form expression, you will be getting this expression K matrix into U matrix. Remember that I'm writing the K matrix in square bracket because it is going to be a square matrix, and also the stiffness matrix is always going to be a symmetric matrix for all types of elements. And I'm representing the displacement matrix by the curly arrow here because the displacement matrix is always going to be a column matrix. And the right hand side of this expression gives me the force matrix. Now you can see clearly that there are two terms on the right hand side. One term is going to give me the force matrix due to uniformly distributed load. It can also give me the force matrix due to uniformly varying load. Okay, in that case this Q will not be a constant. The Q, the rate of loading, may vary in a linear fashion. All right, now the second term in the force matrix, that is going to give me the force matrix due to point load. So today what we are going to do, we are going to derive the force matrix due to uniformly distributed load, and also we are going to derive the force matrix due to point load. So let me first derive the force matrix due to uniformly distributed load. So the expression for the force matrix due to UDL, it is integral over the limit 0 to L, and if it is a Bohr element, it is a quadratic Bohr element which has got three nodes. This is going to be nodal point number 1, this is going to be nodal point number 2, and the third nodal point is right at the center, that is nodal point number 3. And if it is a cantilever, I'm sorry, not a cantilever Bohr, it is a Bohr element that is subjected to uniformly distributed load, that is given by this small little arrows here, and that rate of loading is Q. So that is Q, and W is the weighing function, and in our case this weighing function is going to be the same as the shape functions. So I have got the expression for shape functions here, and also there is W suffix I there, which means that I can take the values 1, which means that Wi becomes W1, which indicates the first shape function. If I put I is equal to 2, I'll be getting the second shape function. I have to use the second shape function. If I put I is equal to 3, I have to use the third shape function. So first I will be substituting I is equal to 1, 2, and 3. In that case, I will be getting 3 equations, and each of those equations I'm going to write them in a single matrix. All right, and you also remember Wi, when wi is equal to 1, it means w1, it means that it indicates the first shape function, and that is associated with nodal point number 1. When I is equal to 2, it indicates the second shape function, and that is associated with nodal point number 2. I is equal to 3 indicates the third shape function, and that is associated with nodal point number 3. So when you have the force matrix, it's going to be like a 3-bar-1 matrix. So you'll be getting the force matrix, the force that is acting at nodal point number 1, and the force that is going to act at nodal point number 2, and also the force, okay, this is going to be the force that acts at nodal point number 2, and also the force that acts at nodal point number 3. Right? So this is the force at nodal point number 1, this is the force at nodal point number 2, and this is the force at nodal point number 3. So this is what we are going to get first. Okay, here in our case the rate of loading is a constant, so in this expression I can get this q outside the integral. I can write it outside the integral, so it's going to be integral over the limit 0 to L wi into dx. So what is going to be our first shape function, which is going to be the same as our weighing function? So I can write this expression as integral over the limit 0 to L. It is going to be n suffix I into dx, because wi is nothing but the weighing function with the weighing function is nothing but the trial solution with the constants removed. So trial solution with the constants u1, u2, u3, when they are removed, they are what you are left out with the weighing functions, which are the same as the shape functions, right? So here we go. Our shape function expression is here. So let me do that. It is q into integral over the limit 0 to L. It is wi, which is the same as ni. In our case, it is the first weighing function. It is going to be 1 minus 3x over L plus 2x square divided by L square. Of course, you are going to integrate this with respect to dx. All right. So it is going to be q integral over the limit 0 to L. Okay, now I can just integrate this particular expression now. So let me do that. If you integrate this particular expression, and I'm also going to substitute the limits directly, so you can check it through in the privacy of your room. If I integrate 1, it becomes x. Upon the substitution of limits, it's going to be L minus, if I integrate and substitute the limits here, it is going to be 3 by 2 into L. If I integrate and substitute the limits here, it's going to be 2 by 3 into L. In the next step, I'm going to get q. If I take the LCM, it's going to be 6, so it's going to be 6L minus, it's going to be 9L plus 4L divided by 6. It is, in the next step, it's going to be q into L divided by 6. So that is what we get. We can call this as equation number 1. I get this by putting I is equal to 1. So I use the first shape function in order to get the first equation in the force matrix due to uniformly distributed load. Now let me substitute I is equal to 2 and let me get the second force term. So here we go. When I substitute I is equal to 2, what I get is it is going to be q integral over the limit 0 to L. It is going to be n2, which is minus x by L plus 2x square divided by L square. Of course, I'm going to integrate this with respect to dx. I'm going to integrate and substitute the limits directly. So what I get is minus L divided by 2 plus 2 by 3 into L. If I simplify this particular expression, it's going to be, I'm just going to take the LCM. So I'll be getting minus 3L plus 4L divided by 6. So I'll be getting QL divided by 6. I'm getting the same expression. This is the force that is going to act at nodal point number 2 due to uniformly distributed load. So let me substitute I is equal to 3. So in the next step, for I is equal to 3, W suffix I becomes W3, which is the same as N3, the third shape function. And the third shape function is 4x by L minus 4x squared by L squared. So it is 4x by L minus 4x squared divided by L squared. So the expression for the force matrix, it is going to be integral over the limit 0 to L. It is Q into N3, which is 4x by L minus 4x square divided by L square into dx. So what I'm going to do is I'm going to integrate and substitute the limits directly. So if I integrate and substitute the limits directly, so I'll be getting 2 by L minus 4 by 3L. Alright, so if you integrate and substitute the limits, the first term, it's going to give you 4L square divided by 2. So I just simplify that. I get 2 by L minus, if I integrate this and substitute the limits, so I'll be getting 4 by 3L. So let me simplify this. The LCM is going to be 12. So I'm sorry, the LCM is going to be 3. So I'll be getting 6. I think I just made a mistake. I'm sorry. Let me do this integration again. Sorry about this mistake. So let me repeat this. It is going to be integral over the limit 0 to L. So when I integrate and substitute the limits directly, I will be getting 2L minus 4 by 3L. So if I simplify this, I'll be getting, the LCM is going to be 3. So it's going to be 6L minus 4L. It's going to be 2L divided by 3. So I can write this as 2 by 3 into QL. So this is going to be the force that is going to act at nodal point number 3. So let me write the three equations in the form of a matrix. So I'll be getting N1, N2, N3. All right. So that is what I'm going to do. So writing the 3 expressions in the form of a matrix. So the expression for the force matrix, the first equation, it is going to give me QL divided by 6. This is the force that is going to act at nodal point number 1. The second equation is QL divided by 6. This is the force that is going to act at nodal point number 2. And the third one, it is 2 by 3 QL. This is the force that is going to act at nodal point number 3. So when you have a quadratic bar element with 3 nodes, node 1, node 2, and node 3, now you know the force that you have to put at nodal point number 1, and the force that you have to apply at nodal point number 2, and the force that you have to apply at nodal point number 3. These are the forces that are acting at the nodal points due to uniformly distributed load. Now we are going to find out the expression for forces due to point load. So here we go. What is the expression for point load? That is given by this expression here. So this is going to give the expression for force matrix due to point load. So let us do this. So the force matrix due to point load for a quadratic bar element, it is Wi into Ae into du by dx. What is Ae into du by dx? It is a solid concentrated load, capital P. So how do I say that? Because you see, the expression for stress is load by area, a solid concentrated load. Okay, not UDL. Capital P here stands for the concentrated load. Okay, and strain is du by dx. So Young's modulus is stress by strain, so it is P by A divided by du by dx. So if you work out for capital P, you are going to get Ae into du by dx. So in this expression for weak form, this Ae into du by dx represents capital P. It's a solid concentrated load. It's not UDL. It's a solid load that acts at a particular nodal point. So it's a concentrated load that acts at the nodal point, not uniformly distributed load, right? Fine. Now I'm going to substitute for I is equal to 1, I is equal to 2, I is equal to 3 in exactly the same manner what I did before. So when I substitute I is equal to 1, so I'll be having the first shape function. The first expression for first shape function is 1 minus 3x by L plus 2x squared divided by L squared. It's 1 minus 3x by L plus 2x squared divided by L squared into capital P over the limit 0 to L. When you substitute the upper limit, which is L, this expression is going to become 0 because the L's are all going to cancel out. You'll be getting 1 minus 3 plus 2, and 1 minus 3 plus 2 is 0. So when you substitute minus of the lower limit, you'll be getting minus of, you substitute the lower limit, this term, when you substitute the lower limit, it just becomes 1 because the rest of the two terms become 0. And when you substitute the lower limit, the capital P becomes capital P, the concentrated load at x is equal to 0. Okay, so substituting the upper limit is the entire term becomes 0. When you substitute the lower limit, this term becomes 1 and you get capital P, the concentrated load at x is equal to 0. Okay, so you actually measure x from here. X is equal to 0. This is going to be x is equal to L. All right. So this is the force. This is going to be our first equation. Now, let me substitute for I is equal to 2 and let me see what I get. This negative sign can indicate the reaction at x is equal to 0. We will see that. So for I is equal to 2, the expression for now becomes minus x by L plus 2x squared divided by L squared. It's minus x by L plus 2x squared divided by L squared into capital P over the limit 0 to L. So when you substitute the upper limit, what happens to this expression? It's going to become minus 1. When you substitute the upper limit, it's going to become minus 1 plus 2 into capital P at L, the load at x is equal to L. When you substitute the lower limit, it just becomes 0. So what happens to this expression now is it is capital P at x is equal to L. So that is our equation number 2. Now let me substitute I is equal to 3 and let me see what happens to the expression. When I put I is equal to 3, I have to use the third shape function. So the third shape function here, it is 4x by L minus 4x squared divided by L squared. It is 4x by L minus 4x squared divided by L squared into capital P over the limit 0 to L. So when you substitute the upper limit, so it becomes 4 minus 4, it is 0. When you substitute the lower limit, it also becomes 0. So you finally get 0. So that is going to be our equation number 3. So writing the three equations in the form of a matrix, you will be getting minus capital P at x is equal to 0. It is going to be capital P at x is equal to L. It is going to be 0 at x is equal to L by 2. So this is the force that is going to act at nodal point number 1. This is the force, concentrated force, that acts at nodal point number 2. This is the concentrated force that acts at nodal point number 3, which means that if this is the quadratic Borel element, this is nodal point 1, this is nodal point 2, this is nodal point 3. You see that this can be the reaction. This can be the concentrated solid force point load that acts at x is equal to L. And this is the node at midpoint, that is the force matrix, it is 0, which means that the quadratic Borel element doesn't allow a concentrated load at the mid nodal point, which is interesting. So this is the force matrix due to point load, and you can see that this is the force matrix due to uniformly distributed load. This is the force matrix due to point load. Hope this video is useful. Now you have got the stiffness matrix, the displacement matrix, and the force matrix. You can mesh the structure by using quadratic Borel element. You can find the values of nodal displacements, stresses, and strains. Hope this video is useful. Thank you all for your patience.